In order to learn the coefficients W hat from data, we have to define some kind of quality metric so that the coefficients give you the highest quality. That's what W hat is supposed to be. So if we go back to our learning loop, we're giving some training data, we squeeze it through some, from feature generation or feature extraction system that gets to h of x, in our model's logistic regression model, we're now going to talk about the quality metric, which is going to feed into our machine learning algorithm that's outputting W hat. So we're dealing with this orange box over here. In particular, we're going to be given some training data as input, and the data is kind of like the one I'm showing. So it has, for example, if you only had two features, the number of awesomes, the number of awfuls, and the output label or sentiment, which might be +1 or -1. Given all this data, the m data points, let's say 1 million data points, we're going to use some kind of learning algorithm that optimizes the quality metric to give us W hat. So what's that quality metric look like? Let's get right into it and try to understand what the likelihood function that we hinted at in the previous module is really about. Let's take our data set, just for intuition, and split it into the data points that have positive sentiment on the right and the data points that have negative sentiment on the left. So we have two tables, there's slightly more negative sentiments and positive sentiments in this example. So what do we want W hat to satisfy, like a good W to satisfy? For all the positive sentiments, for all the data points of positive sentiment, in the extreme, we'd want the probability that it is positive to go all the way to +1. For all the negative ones, we want the probability to go all the way to 0. So it's not positive, it must be negative. So our goal is to find a W hat that makes this possible, or as close as possible. So in other words, if we take the negative examples and the positive examples, there might not be a W hat that achieves exactly 0 for the negative, 1 for the positives, for all of them. And so the quality metric or the likelihood function tries to figure out kind of on average, it measures the quality throughout all the data points with respect to coefficients W. However, we're making kind of extremes happen. Now, if I have the likelihood function, I can evaluate multiple lines or multiple classifiers. So for example, for the green line here, the likelihood function might have a certain value, let's say 10 to the -6. While for this other line, where instead of having W0 be 0, now W0 is 1, but the W1 and W2 coefficients are the same, then the likelihood is slightly higher, 10 to the -6. But for the best line, which maybe sets W0 to be 1, W1 to be 0.5, and W2 to be -1.5, then the likelihood is the biggest, which in this case is 10 to the -4. Now, you've seen these numbers, they're kind of weird, 10 to the minus something, but this is what likelihoods will come up to. They're going to be very, very small numbers, they're going to be less than 1, but the higher you get, the closer you get to 1, the better. And so the question is, how do we find the best W's, the best classifiers? We'll find the ones that make this likelihood function that we're going to talk about as big as possible. So we're going to define this function L of W, and then we're going to use gradient ascent to find W hat. And you should have some fond memories, or maybe some sad memories from the regression course where we talked about gradient descent, and we explored the idea of using gradient to find the best possible parameters to optimize the quality metric. And we're going to go through that in this case again.